Hey everybody, my name is Abel Nieto. I am a PhD student at Aarhus University, presenting some work today on modular verification of CRDTs. So that stands for conflict-free replicated data types, so the kind of distributed data structure. This is joint work with Liam Goldman, Alban Reino, Amin Timani, and Lars Birkedal at Aarhus University. So this work on CRDTs is motivated by the CAT theorem. Essentially, the CAT theorem says that in a distributed data store, you can't have all of the following: consistency, availability, and partition tolerance. Usually this is presented as like choose 2 out of 3, but more accurately, partitions are unavoidable. And so you really have to choose between, do you want your data structure to be strongly consistent, or should it be available, right? But not both. And so what the distributed system community have come up with in the face of this impossibility result is different consistency models that are weaker than linear stability, basically. So one of them is called strong eventual consistency, or SEC, and so this trades consistency in favor of availability. And so basically, what you say is that if you have a data structure and it's replicated, then different replicas are allowed to diverge, so they can be in different states, but they must eventually converge. And so that can be kind of broken up into 2 parts. There's a likeness component to that property, where you say, well, updates have to eventually reach all correct replicas. And then there's a safety component, which is that if you have 2 replicas that have received the same set of updates or events, then they have to be in the same state or equivalent states. And so it's this safety property is sort of what we care about in our work. So it's called convergence, as well as functional correctness, as we will see later on. And so these CRDTs are a class of distributed data structures that have this strong eventual consistency property. So here's a very simple example of a so-called operation-based CRDT. And the prefix is because there's another kind of design class of CRDTs that works in a different way. In any event, so this is a counter, right? And so this counter in this case would be replicated over 3 nodes, ABC. And so because it's replicated, we need a way to propagate operations as they happen, right? So maybe the user executed an increment operation in node A, so the increment is counted by 10. That operation returned immediately to the user. This is why we mean that, so there's no synchronization, right? This is why they sacrifice consistency. And sort of temporarily then node A, might be in a different state at B and C. But then because of that, there needs to be a way for node A to propagate its updates to B and C. There are so by setting things up in this way, you impose some requirements on the underlying communication protocol. Specifically, you need now a at most once delivery mechanism. And so the reason is easy to see. I mean, if you normally in a network you can have duplicated messages and drop messages, right? So in this case, if you were to send this increment to, let's say, from A to B, but your delivery protocol does not guarantee at most once delivery, maybe the increment will get sent twice, right? And so now A and B are out of sync in a kind of hopeless way. And so so many things can go wrong in the network. Your message can be duplicated, reordered, etc. So so to address all of this, so we have implemented in OCaml and verify in Aneris, which is a distributed separation logic, deeply embedded in COC, a framework for building operation-based CRDTs. And we use this framework to implement a bunch of examples, including some higher combinators. And so to our knowledge, our specifications are the first to be both modular and about runnable implementations, right? And so by modular, I mean that once you have verified your CRDT, you can take some totally unrelated program that is a client of the CRDT, and you can use the specifications for the CRDT to prove that bigger distributed system correct. And by runnable implementations, I mean that the CRDT is not modeled as a state transition system, which is a kind of common thing in other related work. But instead, you write it up. In this case, OCaml, you have a realistic programming language with mutation, no local concurrency, etc. And then you're verifying that. Right. And so our implementation, I guess, as we'll see here, so basically, so this is how things are set up. This is an overview of the project. So it's all done in Aneris and verified in COC. Sort of moving one level up, we have a library for what's called Reliable Causal Broadcast, which is this a protocol for guaranteeing both at most once delivery, but also guaranteeing that the order of operations as they're delivered satisfies causality. So this is the happens before relation on distributed systems. And on top of that, we have verified a library for implemented CRDTs, which has the nice property that you basically can implement your CRDT as a purely functional data structure. You pass it into the library, and then the library kind of centralizes all of the nuts and bolts of intra-node local concurrency, sending network operations, so all of the nitty-gritty details, and then you get out a fully fledged CRDT. I'll say a little bit more about that in a bit. Right, so what do you need to go from a purely functional data structure to a CRDT? So let's say we start with a purely functional counter. So a counter has an initial state, let's say 0, and then you need a function effect that goes from the current state of the counter, call it C, to a new state C plus N, given that we have received an operation N, right, to increment the counter. So to turn that into a CRDT, we need a way to propagate all these operations, right? So all of these increments, and to do so while respecting causality and while making sure that messages can't get dropped and reordered. So this is why we have implemented this causal broadcast protocol. We need a way to concurrently apply remote operations. So the user might be doing something on the CRDT locally while a remote operation arrives, right? So there needs to be a way to synchronize these things. And a way to manage mutable state if your implementation uses mutable state, like ours does, which is all of these things is sort of what the library called OpLib provides for you, so that the user can just focus on the purely functional implementation. So so this is OpLib. So this OpLib library that we have implemented on top of the causal broadcast protocol has two interfaces. There's an internal interface for the CRDT implementer. And they have to provide this initial states for the CRDT and this effect function, and they also have to prove a number of properties for those. And then there's an external interface, which is for the user of the CRDT. And so what they get back out of the library is two functions: a function to query the state of the data structure and a function to update the state of the data structure. But now it's not just like a purely functional implementation. Now it's this propagated data type with all these other properties that I mentioned. Just to give you like a very quick flavor of the kind of specifications that are available to the user of the CRDT. So this is the external specification. So this is the spec for get state. Like in order to call get state, so like a separation logic. So the spec is giving us a horse style specification. So to call get state, what do we need? We need to provide a resource called log state ISH, and so the kind of intuition for this resource that we have constructed, and that basically a lot of the work went into constructing these resources with the right properties. It basically gives you knowledge that replica I has received some events that are in two sets of events, S and H. So these events are the set of operations that are in the data structure. And so here it segregates between own events and foreign events. So the own events are the local events that have been performed by replica I, and the foreign events, which is H, are the foreign events that have arrived from other replicas. And so that's in the precondition, and then after calling get states, your logical knowledge has now changed, so that you get a log state of the same S, but then you get an H prime, which is a superset of H. And so what this signifies is that while the set of local events has not changed, because you have not performed any local operations, the set of remote events might have changed, because in the background, the data structure might have been delivering some additional remote operations that kind of came from other replicas. And finally, that the return value from calling get state, so the value that you get out of the CRDT, is a function of the set of events that have been received. And so this bracket notation that we see here. This is a so-called denotation, which is a specification style for CRDTs from prior work that basically allows you to specify the CRDT as a function from a set of events together with some causality metadata that is not used, for example, for the counter example is not necessary, but it's used in other examples. And so you get this very nice sort of abstract level description of the CRDT And so this is nice because while a lot of the work on verifying CRDTs focuses on eventual consistency doesn't tell you the whole story, because you also want to know, functional correctness. You want to know what is it that the data structure is doing. Like a counter behaves like a counter, and a set behaves like a set, and so on. Right. So that's the library, and then the implementer of the CRDT, in order to use the library, has to provide this initial state in this effect function, and they have to prove a number of properties that are shown on the left. But the important part is that they have to show in some way that the effect function that they are providing, which computes sort of updates to the state of the CRDT, agrees for some notion of agrees with the denotation, with the abstract specification. And so once they have the implementation of effect and init and the proofs that they agree with the denotation, they can sort of feed that into the library, and then you get out the different CRDTs. And so this is kind of a list of the examples that we have implemented. So we did 12 examples, including some CRDT combinators for product and map. And so the neat thing about all of this is that we actually got to this project in a kind of roundabout way, where a few years ago we implemented a causally consistent distributed key value store. And what we realized is that we could kind of repurpose different elements in those proofs and the notion of causality that we had developed there in this more general setting of the CRDTs. And so one of the examples that we have now is this table of last writer wins registers. The last example here, which is very, very close to that kind of ad hoc implementation of the key value store that we had a couple of years ago. And in this case, you can get to it by applying the map combinator to some other to the last writer wins register, which is another kind of CRDT. And you can see that I mean the overhead in general for these kinds of proofs is like 10x to 40x from number of lines of code to number of lines of proof. But the nice part is that that last step where you get the table, the using of the combinator really kind of factors out complexity, and it's relatively straightforward to instantiate things once you have all different components. So we really kind of double down on the modularity theme. Right. So in conclusion, so we've implemented in OCaml and verified in Aneris a framework for building these operation-based CRDTs, as well as a bunch of examples. To our knowledge, this is the first foundational proof of correctness and eventual consistency for the CRDTs. And so by functional correctness here, by foundational here, I mean that we go sort of all the way, right? So we implement the causal broadcast, and then on top of the causal broadcast, we'll build the CRDT, as opposed to assuming that the network satisfies, like gives you a causal broadcast as a primitive. And that our technique is the first thing that is both modular, but also about realistic implementation. And that is all.
So Jonathan asked, your technique is compositional in the sense that larger CRDTs can be constructed from smaller ones. Does this make both proofs and code shorter, or only one of the two?
Right. Yes. So okay. So compositional. Right. So I think so. The technique is compositional in more than one sense, right? So one sense is precisely that you can use these combinators to build, from smaller CRDTs, you can build like larger CRDTs, right? Another sense, which I think is sort of equally important, in which the technique is compositional, is that you can take you can take a proof of correctness of a CRDT, and you can combine that with a proof of correctness of a client that is verified against the specification of the CRDT, and then you can make you can build you can take the entire system now, and you can have a proof that is correct, right? So you're not limited to proving that CRDTs specifically are correct. You can reason about anything you want. I mean, anything that this Aneris logic allows you to reason about. Does this make both proof and code shorter? Only one of the two. So if we're talking just about composing CRDTs, yes. So this makes both proofs and code shorter. Yeah, and the example is, well, I mean, the code is shorter, for the normal reasons, right? So you can compose things in code, and the proof is also shorter because you have to prove less, right? Like in our case, we have this table that maps some keys to some registers, and you know, once you have the proof of the register CRDT, you know, now you can sort of just plug it in, right? Yeah, does that answer the question? Or
I think it does. At least it makes sense to me.